In the endless reaches of the universe, Earth seems unique. It's a planet shaped and molded by life. A planet that 6 billion people call home today. But when it was born, some 4.5 billion years ago, Earth was a violent place. So hostile, it's hard to believe life could ever begin here. Covered in lava and smothered in noxious gases, Earth was a planet under siege.
If you were a human going back into time and trying to stand on the early Earth, it would be just like visiting a planet that was not your own.
This was a hazardous world, no doubt about that. If you were located in the wrong place at the wrong moment, you were simply vaporized.
It was a planet plagued by catastrophe. If you condense all of Earth's history to just 24 hours, then only minutes after it formed, the entire globe melted and reformed. Then, to make matters worse, another planet about the size of Mars slammed into Earth. A cataclysm that created our moon. But soon after these disastrous beginnings, the most radical transformation of all time hit the planet. The origin of life. So how did life begin? Well, over the years, people have come up with some pretty creative answers to this question. One of my favorites comes from a 17th century scientist who wrote down a recipe for creating life from scratch. Let's see. It says here, take a dirty garment, place it in a vessel. Next, add wheat. Then, according to the recipe, after fermenting for 21 days, mice will appear, fully formed. Of course, we all know that life doesn't form this way. But at some point in Earth's early years, life did emerge out of non-living ingredients. And for clues to the real recipe of life, we have to go back some 4 billion years to a time when Earth was nothing like the planet we know today.
When we think of early Earth, we must recognize it was not a Garden of Eden. There were no clear blue oceans. There was no clear water. There were no plants. There was no life at all.
The young sun was weaker than it is today. And its light barely penetrated the atmosphere of carbon dioxide, spiked with the pungent fumes of hydrogen sulfide.
Since the atmosphere was thicker and dominated by CO2, the Earth had a reddish tinge to it. It didn't have the familiar blue sky. The oceans would have had an olive green color rather than our familiar blue color.
For about the first 600 million years, comets and asteroids pounded our planet. A time known as the heavy bombardment. These interplanetary missiles measured up to 300 miles across. Their impacts vaporized Earth's oceans and melted its crust. With its extreme temperatures and toxic rain, seemingly nothing could survive here. But we now think that in this hellish environment, life first took hold. And today, hidden away in remote corners of our planet, conditions that in some ways resemble the extremes of early Earth can still be found. Penny Boston and Diana Northup are microbiologists on an expedition to investigate how life can survive in those harsh surroundings. Buried in the depths of this tropical rainforest is a cave called Cueva de Villaluz. Located in southern Mexico, it's an underground world laced with hydrogen sulfide, a foul-smelling gas that was present on Earth some 4 billion years ago.
These relic or antique environments like Cueva de Villaluz offer the same kinds of environments that we would have found on early Earth, and we're hoping to get clues to work backwards from those. As you approach the cave, you begin to get these faint whiffs of the rotten egg smell, and as you get closer, this becomes more intense.
Hydrogen sulfide can be extremely poisonous. So the scientists have to wear gas masks inside the cave and carefully test them for leaks.
No leak.
Have you got everything in there?
I think I got everything. Yeah.
At the levels at which humans can't live very long in hydrogen sulfide, you don't smell it at all. And it will just simply cause you to go unconscious and die very quickly.
But can any other forms of life survive in the deep recesses of the cave, so toxic to humans? Here, hydrogen sulfide, an invisible gas, escapes from the underground springs, reacts with oxygen in the water, and coats the cave with sulfuric acid.
The longer it sits there on the walls, the more acid it becomes, and so eventually by the time the drop is falling on you, it's a very, very acid environment.
The slime layer feels pretty thick today.
It's very fatiguing, and even with the protective masks that we have, we pick up loads of toxic gas through our skins and perhaps through tiny leaks.
Oh, get them out of those sweat tights to your left. Oh, yeah.
Amazingly, despite the extreme conditions, it appears that life is thriving inside the cave. It comes in a strange package, colonies of single-celled bacteria that form slimy drips scientists call snotites.
The snotites are drippy, gooey, mucousy formations that look like stalactites, and that's why they were called snotites, but because they resemble strings of snot. We believe that the snotty, gooey stuff is to protect them against extreme acidity, because when we measure the drips on the snotites, they are as extreme as battery acid. And so while we find that daunting, this is where they thrive.
Bacteria are among the most primitive and most common organisms on Earth. Like all forms of life, they grow, adapt to their environment, and reproduce. Inside each single-celled bacterium is a molecule of DNA, the code of life, which allows them to multiply. There are millions of bacteria in each snotite. And down in the underground streams, Penny Boston has found different kinds of bacteria in slimy clumps she calls phlegm balls. In fact, the cave is home to a huge number of bacterial colonies. And astonishingly, instead of being poisoned by the hydrogen sulfide, these bacteria depend on it for their survival.
They take the hydrogen sulfide and they get chemical energy out of it. It doesn't poison them, it's home sweet home for them. And this is a pretty new finding for these organisms.
Conditions on early Earth may have been far worse, But these bacteria suggest that primitive life could have thrived in extremely hostile environments. But where did the very first life come from? For more than a century, scientists have known that life is the result of chemistry, the combination of just the right ingredients in just the right amounts. Today we know these ingredients aren't things like dirty garments and wheat, which people used to think would spontaneously generate mice. Ingredients of life are actually much simpler. All living things, from bacteria to mice to you and me, are made from a small set of chemical elements. Hydrogen, oxygen, carbon, nitrogen, 4 of the most common elements in the universe. Combined in just the right way, these are the fundamental ingredients of life. And carbon is the star of the show.
Carbon's everywhere. It's all over the universe.
What makes carbon special is the kind of bonds that it makes, both with itself and with other elements.
We know of no other atom that has the flexibility that carbon has to form diverse types of compounds.
And the idea that life could have started when carbon and other ingredients combined in the harsh conditions of early Earth was first put to the test in the 1950s by a young graduate student named Stanley Miller. To simulate the newborn Earth in the lab, Miller assembled a contraption made out of flasks and tubes. He filled one flask with gases thought at the time to represent Earth's primitive atmosphere, and he connected that to another flask with water to represent the oceans.
And then he did a brilliant thing. He simply put an electric charge through that to essentially simulate lightning going through an early atmosphere. And after sitting around for a couple of days, all of a sudden there was all this brown goo all over the reaction vessel. And when he analyzed what was in the vessel, now he actually had amino acids.
Amino acids are compounds that form when molecules of carbon and other elements link together. They are the essential building blocks of proteins and cells, vital ingredients of all living things. Stanley Miller's experiment was headline news and jump-started the scientific search for the origins of life.
Life is really chemistry. There's no question about that. In fact, it's a chemistry that when you get the recipe right, it goes, and it goes fairly quickly.
That recipe is hotly debated today. And most scientists think the environmental conditions on early Earth were very different from the ones Miller simulated in his lab. And another debate rages about when this recipe first got cooked up. On our 24-hour clock, the barrage of asteroids and comets lasted from about midnight until almost 3:30 in the morning. The assault then weakened, but continued for more than 100 million years. It's hard to believe that life could have gained a foothold during this unstable period. But new discoveries reveal that life may have existed as early as 4 in the morning, or about 3.8 billion years ago. The evidence comes from some of the oldest rocks on the planet, found in the remote regions of West Greenland.
The geology of Greenland is unique. It contains a record of some of the earliest geological processes that we know of on the Earth. The rocks themselves are thought to be between 3.7 and 3.9 billion years in age.
These rocks are so old that any fossils they once contained have been destroyed. So, to find out if life existed when they formed, Moisish had to look for evidence that is far more elusive.
There may have at one time been small fossils, microfossils, but under the conditions of heat and pressure that these rocks experienced, such fossils would have been disaggregated and destroyed. So what we have left behind then are chemical fingerprints of ancient bacteria or microbes.
To search for those fingerprints, Moisish first extracts a sample from the ancient Greenland rocks. Then, he will analyze its chemical composition, looking for carbon, a signature of life. But carbon comes in several different forms. And Moisish wants to know if the carbon in this sample is the kind left behind by living creatures. If so, he believes that life may have existed when these rocks formed over 3.8 billion years ago. A controversial claim.
It was a surprise for us to find evidence of ancient life in these rocks. We didn't know if it would be there. You know, just because the stage is set doesn't mean that the actors are present. But these samples here represent the first evidence we have, direct evidence of a biosphere on our planet.
If it emerged so early, life was lucky to miss the greatest cataclysm of all time. An impact like no other in our planet's history. It happened when another rocky sphere about the size of Mars collided with Earth. The outer layers of our planet were vaporized, and the debris from this collision coalesced to form the Moon. That impact was so powerful that any building blocks of life that existed on Earth would have been destroyed. This gives rise to speculation that the ingredients of life didn't form on Earth at all, but arrived special delivery from outer space.
From its size and its appearance, this thing came from outer space. I even have reason to believe that there's some form of life in it.
Hollywood has always been taken with the idea that life came from outer space. But it's not as far-fetched as it might sound.
Space is not very far away. Space is only about 20 kilometers that way. Now that's very close, and space is vast.
And a scientist named Don Brownlee designed an experiment to find out if space might actually harbor the building blocks of life.
There are 40,000 tons of bits of comets and asteroids that impact the Earth every year. This is mostly in form of particles that are less than a millimeter in size. We breathe them, they're in the food that we eat, but they're very difficult to find. You can only find them in very special places.
To see if this shower of space dust contains the ingredients for life, Brownlee needed to obtain samples uncontaminated by Earth's atmosphere. So, to get just a few micrograms of dust, he commissioned a former spy plane to fly close to the edge of Earth's atmosphere. Sticky pads on the plane's wings collected the space dust. Then, Brownlee's colleagues sliced the dust particles into slivers less than 1/10 the thickness of a human hair. And they discovered that these tiny particles are rich in the seeds of life.
When you look at them in an electron microscope, it's this wonderful array of minerals and carbon and organic materials that are 4.55 billion years old, and we believe are the building blocks of life.
And this extraterrestrial dust isn't the only possible source of life's ingredients. In a region of space called the asteroid belt are huge amounts of debris left over from the formation of the solar system. And sometimes, chunks of debris containing metal and rock fall to Earth, bearing surprising gifts. One such meteorite landed in the town of Murchison, Australia in 1969.
It's a gold mine, this little chunk of meteorite which fell on Australia last year. For the past 6 months, they've been taking it apart and have discovered it contains amino acids, the building blocks of life.
It was the first time that complex organic compounds had ever been found in material from space. And if meteorites like it were common, perhaps they had delivered vast quantities of the original constituents of life to early Earth.
Enough organics are present here that we think that meteorites like this provide to the early Earth its entire budget of organics. So all the organics in your body, all the carbon in your body, and in your lunch you had today, arrived on the Earth in meteorites like this. If they come in the atmosphere in large enough objects, they're like little capsules coming in the atmosphere. They break apart on the Earth's surface and deposit their cargo of organics.
More than 70 kinds of amino acids have been found in meteorites. And many are the fundamental ingredients of proteins that make up living cells. During the heavy bombardment, millions of meteorites may have seeded the Earth with the stuff of life. And there might have been an even more efficient delivery system. Comets are like giant dirty snowballs made of ice and rock. Some comets that hit the early Earth were the size of mountains, and a large portion of their mass could have contained organic compounds. The destructive power of comets and meteors is astronomical. The meteor that slammed into Earth some 50,000 years ago, here in Arizona, blasted a hole in the ground nearly a mile wide, from here to here, and so deep it could hold a 60-story skyscraper. And as if that weren't enough, the force of the impact was so great that it instantly vaporized nearly the entire meteor. 300,000 tons of it. So it makes you wonder, if the building blocks of life were delivered courtesy of comets and meteors, could any of the tiny ingredients they carried have survived the landing? And just what happens to things like amino acids when they slam into Earth with such devastating power? To answer those questions, one scientist came up with an ingenious experiment. Using a huge gas-powered gun,
That's good, stop.
Jennifer Blank simulates the extreme pressures and temperatures that are unleashed when a comet smashes into Earth.
We set out to test whether or not the materials would survive or whether they would break down. And we expected that, or we were hoping that some fraction would survive. And we figured the parts that didn't survive would break down into smaller components. But in fact, what we found was much more exciting.
The gun fires a bullet at 5,000 miles an hour towards a sample that represents the organic molecules inside a comet. The sample consists of a solution of 5 different amino acids, 2 of them present in every living cell. The mixture is inserted into a steel capsule. The gun will send a shockwave through the capsule, simulating the extreme pressures of a comet's impact.
I think it's very hard to just imagine what kinds of pressures were generating these experiments. If you think about going to the bottom of the ocean, the pressures you'll have there are only 100 times atmosphere. So these are hundreds of thousands of times atmospheric pressures.
Will Jennifer Blank's experiments show that the building blocks of life can survive a crash landing on Earth?
Clear the room.
Okay, charging up. Okay, bringing up the X-rays. Okay, I'm going to external group. Ready to fire?
Go ahead.
Okay, then 3, 2, 1, fire. 3, 2, 1, fire.
When they remove the capsule, it's undamaged. But have its contents survived the impact? The once clear solution of amino acids has turned a tarry brown color. And the analysis revealed that not only had the material withstood the colossal pressure of the impact, but it had transformed into a new compound. Amino acids, combinations of carbon and other basic elements, had fused together to form more complex molecules called peptides.
We went from our initial small compounds, and here's an example of one of them, simple amino acid, and we used the energy associated with the impact to build larger molecules. Molecules like this. This is a peptide, and we showed that we could use the impact energy to grow larger molecules from the simplest building blocks of life.
Peptides link together to form larger building blocks, proteins, which make up all the cells in our bodies. But the leap from non-living ingredients to a living creature, complete with DNA which allows cells to replicate, is staggeringly complex. No one knows how this process started or what course it took.
It is hard to really get your head around the great leap from non-living to living.
Well, it's hard enough that nobody's succeeded in doing it in the laboratory.
I think it's an astonishing mystery and one that we truly don't understand in any great detail.
While we don't yet know how the spark of life occurred, we can try to figure out where it might have gotten a foothold. And because the planet was under such devastating assault from comets and meteors, the leap to life may not have taken place up here on Earth's surface. To take hold, life might have needed a safe haven, perhaps underground. A team of scientists descends into one of the deepest mines on Earth to investigate whether microbial life can survive far below the Earth's surface.
And the mining environment gives us this fantastic window into the deep subsurface. It's a unique scenario because there is nowhere else on planet Earth that allows you to have access to that sort of sample location at 2, 3, 3.5 kilometers deep.
It takes 45 minutes to reach the heart of this South African mine. Conditions here are extremely uncomfortable. For humans, that is. The temperature of the rock is 120 degrees Fahrenheit, and the air pressure is twice that at Earth's surface. Life down here survives entirely without sunlight. If they exist, microbes need to find a way to live in pitch darkness, drawing chemical energy from water and minerals trapped in the surrounding rocks.
Microorganisms have been shown potentially to be able to use these molecules to provide themselves with energy and support themselves completely independent of photosynthesis. And if we can prove that that is the case here, then that's very interesting, because that adds credence to the idea that you could have life originating in the deep subsurface.
As the miners drill into the rock, they break into ancient pockets of water, havens for microorganisms.
We're not sure how organisms can live in such extreme environments. The major thing is there's such low nutrient availability. There's nothing really for these guys to continually use and process to survive, and yet somehow they do. And the question is, how do they do it?
Right, 3, 2, 1, go.
The first step is to collect pristine samples of the water and see if they can grow the microbes it contains.
I get a very big sense of achievement if I can actually take something that's been isolated for 200 million years, put it in the laboratory and actually find out what it is this organism needs to survive.
In a makeshift lab near the mine, the team attempts to recreate the environment deep inside the rock. And they have found that these microbes are dining on a variety of strange gases.
It turns out that in the deep subsurface there's an abundance of methane gas and ethane and propane. Now for you and I that's not a very exciting diet, but what we think is that these organisms may be taking that kind of gas and actually using that as a food to survive.
On such an exotic diet, the bacteria draw just enough energy to divide and reproduce only once every 1,000 years, suggesting a way that life could have survived deep beneath the surface of the early Earth. And Earth's crust may not have been the only place where life could have hidden from the heavy bombardment. Another safe haven may have been the ocean. Volcanic activity was intense on the early Earth. Chemicals from deep inside the planet spewed into the primitive seas. Even today, marine biologists have discovered volcanic vents on the ocean floor. Despite scalding temperatures, acid eruptions, and total lack of sunlight, they found creatures of all types thriving down here. And at the bottom of the food chain are microbes that live on the noxious hydrogen sulfide gas erupting from the vents. On early Earth, primitive life may have survived in similar environments.
If all of the bombardment was occurring near the surface, survivors would be existing in just these kinds of hydrothermal vent communities, where there's abundant water and nutrients and heat and food in the form of chemical energy. It has been found that organisms collected there nowadays are genetically kin to some of the earliest organisms that we think existed on the Earth.
By about 3.5 billion years ago, or 5 o'clock in the morning on our 24-hour clock, the bombardment of asteroids and comets had ceased. With far fewer violent impacts on Earth, microbial life could now survive outside its protective hiding places. After it reaches Earth's surface, life would take advantage of another source of energy, the sun. Up here, microbes evolved a green pigment known as chlorophyll. This allowed them to trap sunlight and use it to drive a chemical reaction that converts carbon dioxide and water into food, called photosynthesis. It was a clever invention that enabled some bacteria to grow and reproduce almost without limit. Once it started, photosynthesis was a runaway success. And today, it's how all green plants make their living. As Earth cooled, this new generation of cells spread across the oceans. Immense colonies of green slime would take over the world, kicking off the greatest transformation in our planet's history.
Photosynthesis is the great liberator of biology. With photosynthesis, the energy is coming from the sun, and life could spread literally over the entire planetary surface.
And this remote corner of Western Australia holds clues to how that happened. These domed structures, called stromatolites, are built up layer by layer over thousands of years by tiny microbes. These microbes may be similar to life forms that dominated our planet billions of years earlier. And in the arid hills nearby, there may be evidence of these ancient creatures. These rocks have remained unchanged for 3.5 billion years. Here, it's possible to walk on the surface of early Earth. Martin van Kranendonk spends months at a time in this wilderness, studying the geology and producing maps. In a secret location in these hills is what could be one of the greatest geological discoveries of all time.
These are the oldest fossils in the world, at about 3.5 billion years old. And they're composed of stromatolites. And at this outcrop we can see two different types of structures that these creatures formed. First are these black mats that have wrinkly textures all through it. And the second are these larger domes that form these broad structures. The most likely way these things formed is by the growth of microbes.
Like modern stromatolites, these ancient structures could also have been built by colonies of bacteria. And not far away are fossilized ripple marks, which suggest they might have grown in shallow water.
And here you can see we've got a smaller structure that we call the Mickey Mouse ears, which is this beautiful doubly branching structure. And there's nothing else that we can think of which would make that except something that was growing on the bottom of the ocean.
So perhaps the ancient stromatolites were formed by microbes like the ones that build these structures today.
These big stromatolites are composed mostly of rock at the bottom, and the only living part of the stromatolite is a thin layer on top. And that thin layer on top is made up of microscopic blue-green bacteria called cyanobacteria.
Named after the blue-green color of their cells, these cyanobacteria use photosynthesis to collect energy from the sun. They secrete a sticky coating to shield them from ultraviolet radiation. As tiny pieces of dust and sediment settle on top of the sticky cells, the bacteria migrate closer to the surface to reach the light. The layers of sediment build up by about 0.5 millimeter a year. These structures contain living microbes, just as they have for thousands of years.
The amazing thing about these stromatolites is that the microorganisms which build them are so tiny. And the structures that you see around me, compared to their size, are enormous. It would be like if humans made a skyscraper that was 105 kilometers high by 70 kilometers across. These are massive structures for the size of the organisms that make them.
Many different shapes and sizes of what appear to be fossilized stromatolites have been found in the rock. It seems likely that these structures were formed by some type of microbe living on the early Earth. Perhaps even by the ancestors of today's cyanobacteria.
We're looking at sort of a cross-section through the top of these cones and the layers that were laid down year after year. And the fact that they're all different sizes on this one surface shows that there was a colony of microorganisms growing on this one bedding plane. And that's really fascinating because it means that life evolved on this planet very early and very fast.
And it's the cyanobacteria that would bring about the most astounding change in Earth's history. A change that could have started as early as 3.5 billion years ago. Over time, stromatolites would spread out across the planet. As a byproduct of photosynthesis, the ancient bacteria produced a waste gas, oxygen. The oxygen was absorbed into the oceans at first. There it combined with iron erupting from undersea volcanoes to form iron oxide particles that fell to the ocean floor. Over the next several 100 million years, the planet literally rusted. There may have been other forces at work, but eventually, all the iron was turned into oxide, building up layer after layer, one of the most valuable mineral deposits on Earth, iron ore. Located in Western Australia, this is one of the world's largest iron mines. The iron here was originally deposited on the floor of a primordial ocean.
Control blast 2, we're at the firing position, stop is connected. We'll fire in 10 seconds with a 5-second countdown. Roger, blast 2.
Every week they excavate 500,000 tons of iron ore, used to make steel for everything from cars to skyscrapers.
4, 3, 2, 1, fire.
In a more pristine state, thousands of ancient layers of iron ore are preserved in the Karajini Gorge, just 30 miles from the mine. The layers exist because different amounts of iron oxide were deposited at different times of the year. Cyanobacteria produced oxygen in varying amounts as water temperature changed with the seasons. All over the world, vast amounts of iron ore were laid down in similar ways. On our day-long clock, this process continued until 1 in the afternoon. Eventually, oxygen produced by cyanobacteria began to build up in the atmosphere. Slowly but surely, this transformed the planet. Over the next 8 hours or so, tiny microbes raised the level of oxygen from less than 1% to today's 21%. The time was about 9 p.m. It's amazing to contemplate, but without cyanobacteria, there would be no oxygen, and Earth would still be smothered in noxious gases. Plants, animals, and humans would have never evolved.
We're sitting here today breathing an oxygen-rich mixture of air. We couldn't be here without that oxygen, but that oxygen wasn't present on the early Earth, and it only became present because of the activity of photosynthetic organisms.
Life has made this environment what we know. It's allowed us to live on the surface. It allows us to breathe. It allows large organisms like we are to function at very high rates of activity.
The oxygen also helped protect life from the sun's lethal ultraviolet radiation by creating a layer of ozone in the upper atmosphere.
One of the fascinating properties of that is that it actually screens out, just sort of like a sunscreen does on your skin, screens out this harmful radiation.
With the protection of the ozone layer, life was able to diversify into more complex organisms. It took only the last 3 hours of the day for all other life forms on our planet to evolve. The first multicellular life emerged at 6 minutes past 9 in the evening. Then came fish and insects and reptiles. By about 10 minutes to 11 in the evening, dinosaurs roamed the earth. The first primates appeared at 20 to midnight. And with less than 30 seconds to go, the first humans made their appearance.
It's only been the last 10% of the Earth's history where there was life on the surface of the Earth that you would see with your naked eye. So for most of Earth's history, life has basically been invisible on the Earth.
Over 1 billion or 2 billion years, the amount of oxygen that these little creatures produced was enough to actually change the entire atmosphere of the planet.
Multicellular life that we're most familiar with, animals, plants, their environment was made possible by the slow, toilsome task of bacteria to oxygenate the atmosphere.
Microbes ruled the Earth for more than 3 billion years, 2/3 of its history. These tiny organisms had transformed an entire planet. Without them, complex life, humans included, would have never evolved.
Stay tuned for more about Origins, a Nova miniseries. But first,
Frontline provides me with information that makes me think.
First I shout at the television. You gotta be kidding!
You won't see this anywhere else.
The stories hit close to home.
Truth is a very valuable commodity.
They're uncompromising. I want to do something. I want to take action. It changed the way I actually live my life. It lets me make up my mind. I trust it. When I watch Frontline,
It makes me angry and it makes me want to voice it.
I want to make a difference. We can make a difference.
Frontline.
These guys are my heroes.
Coming up tomorrow night on Origins, where are the aliens? Nova is on the hunt for answers.
Is our little planet Earth the only place where the action is?
We're definitely not alone. It's inconceivable how big things are. To think that we're alone here is ridiculous.
If extraterrestrial life is really out there, what makes us think we can find it?
We're finding new planets like crazy.
These planets could be much stranger, much more bizarre than any theories that had ever been conjured before.
Then, the ultimate mystery. How did the cosmos come to be? How did the universe cook up the perfect ingredients for life? The cosmic quest starts with a bang, ends with us, and tells a new story of what happened in between.
We are actually on the brink of a revolution of unimaginable proportions.
A scientific detective story takes you back to the beginning of everything. On Origins, a Nova miniseries, tomorrow night on PBS.